Hello friends, in this video I'd like to solve the following problem from the Romanian District Mathematical Olympiad for 11th graders 2011, problem number 2. It is from linear algebra. Let A be an m by n matrix with complex entries. Let B be an n by m matrix with complex entries. And let m be greater than or equal n. Moreover, let the product AB be of rank n, and let AB squared be equal AB. We wish to prove two things. Part A is very easy. Prove that BA cubed equals BA squared. And part B, find BA. Find BA. Actually, if you do B, then A is trivial. And curiously, we will not use result of part A to find BA itself. But here are my hints for this problem. First, notice that BA cubed is BA, 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 BA squared is BA, BA, and notice that we can omit any parentheses right here because the composition, the multiplication of matrices is associative. Moreover, any matrix represents some linear mapping, so we can view, so if matrix A has m rows and n columns, then it can be seen as a linear mapping from r to the power of n to r to the power of m. Likewise, B can be viewed as linear mapping from r to the power of m into r to the power of n. And by the way, I will not distinguish between matrix and linear mapping. It's not very serious conflict of notation, but it should not lead to any misunderstanding. Next, a rank of a product is always less than the minimum of ranks. In other words, when we are multiplying more and more matrices, the rank cannot increase, it can only decrease with any other multiplication. And also, rank is bounded from above by n, since n is less than or equal m. Now, and use the following two facts. Since rank of A, you should be able to show that rank of A is n, rank of B is also n. Notice that A must be injective, B must be surjective. Just look at the dimensions which appear. And also show that for any vector w, we have BAW equals W, which of course means, spoilers, that BA equals the identity matrix. So give this problem a try, and I will see you in just a minute. Alright, so let's start with part A, because part A is very, very easy. Or maybe first let's expand our assumption. AB squared equals AB. It of course means that AB equals AB. Now, part A. What is BA cubed? Well, BA cubed is BA, BA, BA. Alright, and notice that this part, AB, AB, well, by assumption, it can be replaced by just B, AB. Maybe I will write it in yellow. You know what? I will write it in yellow. BA, B, A, B. AB, AB is the same as AB. Well, what is BA, BA? It's BA squared, which closes the proof of part A. Very straightforward. But part B is much harder. Part B. Alright, so let's view our matrices as linear mappings. A goes from r to the power of n into r to the power of m. B goes from r to the power of m into r to the power of n. These are linear mappings. Moreover, notice that we have the following. Rank of A is of course less than or equal n. Likewise, rank of B must be also less than or equal n. Why is that? Well, because, for example, rank of A is bounded by n because the dimension of the domain is n, and rank of B is bounded by the dimension of the codomain. Alright. But now, let's also notice that by assumption, n is rank of a product of matrices AB. And rank of a product is always less than or equal the minimum of rank of A and rank of B. Alright, but since n is less than or equal the minimum of these two ranks, then these two ranks must be greater than or equal n, both of them. Both of them. Now you clearly see that they must be both n. So we have established that rank of A equals rank of B equals n. Now, that is something. But now, let's take our linear mappings once again. Let's take them once again. And now let's take a look. Notice first that there is something known as rank nullity theorem, which says that the dimension of R to the power of n equals the dimension of kernel of A plus the dimension of image generated by A. Image generated by A is of course the same, its dimension is of course the same as rank of A. So now we have the following: n equals dimension of a kernel plus n, which means that kernel of A has no dimensions, it's zero. It's zero. Which of course means that our function A is injective. As it is injective. Alright, what about B? Well, notice that this time B, the rank of B is n, and it's of course the same as the dimension of R to the power of n. So the whole codomain is filled by our matrix, which means that our mapping is surjective. B is surjective. It is surjective. Alright, now we will show that for any, we will basically show that for any vector w from R to the power of n, BAW equals W, which will of course mean that BA equals the identity matrix. So is my claim. So let's take any W from R to the power of n. Since B is surjective, there is V in R to the power of m such that W equals B times V. Alright. Notice now that by assumption, we have the following, that AB, it was our assumption that it equals AB. Well, since this is the case, I will multiply on both sides by vector V. And now let's take a look. What is B times V? It's W. So we have ABA times W equals A times W. Alright, But now remember that this is just the application of some function. So we are taking a with this argument and we are taking a with this argument. A is injective. Since a is injective, we can cancel a on both sides. We have finally BAW equals BAW basically equals W. And since W was arbitrary, this means that BA is the identity matrix. So i.e. BA is n by n identity matrix. And this is our answer for part B. BA equals the identity matrix. N by n identity matrix. And of course, once you know this, you can go back to part A and you can do part A once again, because BA cubed is the identity, BA squared is also the identity. But there is no need to do that, because proof of part A was very simple. So this concludes our entire proof. Thank you very much for watching. I hope that you've learned something new this time. I hope that you enjoy linear algebra, and I will see you next time. Goodbye.